Our friend Patrick Vogel of AltShift is to blame for what you're seeing here. He came up with this weird idea and asked if we could help integrate a few more details in Vellum in this, let's call it, alien mess. And not only did he come up with this disgustingly brilliant idea, he also agreed to us recording a tutorial on it. So thanks so much for that, and let's dive into Houdini and build this. This is a Vellum gore fest, so basically what we're doing here is setting up a bunch of different Vellum constraints and then animating some of those to get this looping type of animation. The first thing we want to do is, as always, drop down a geonode, dive in there, and build our base geometry, which in our case is based on a sphere. Let's use the sphere create because we want to create a polygonal sphere that is oriented along the y-axis. And in this case, we just rotated it to sit something like this in the scene, a bit tilted downwards. We decreased its radius to 0.2 and moved the center up a bit, just so it sits in the scene where we want it to. Decided for 15 rows, 50 columns, like this, and then this thing needs an opening. So we blast just the first point, and now we have this opening here. Next, let's give this a bit of thickness using the poly extrude. And in here, we'll just dial in the distance to our liking. In our case, we ended up with a kind of wonky number just by manually dialing it like this. And if we scroll down here, we want to output the back as well, and also have front and back groups. Next, we'll polybevel this hole here by selecting those two rings here, just going to our edge selection, and then just clicking on the first edge we want to select here, and then holding down the A key, which allows us to do this kind of loop selection here. So let's select first half here, and then just hold down A again, and hold down Shift as well to select the second half of this loop here. And let's do the same thing for the inner loop here. So holding down Shift first, selecting the first edge here, and then Shift and A to select the first half of the loop, and then successively selecting the full inner loop like that. And now over the viewport, I'll just press Tab and start typing polybevel and hit Shift and Enter. So that'll attach the polybevel after our poly extrude and only select the groups we just selected with the edge here. And now we can dial in a distance so we can see only those groups get beveled. I want to increase the divisions to 8 here, making this bevel really finely resolved. And the distance, again, we dial that in manually, so a bit of a wonky number, 0.061, like this. Next, we gave this thing one more subdivision using the subdivide node, like so, just at its default settings, and then put it into a remesh for good measure, which is set up a bit too aggressively here. So let's reduce the target size to 0.024. Again, dial that in manually. So that's where these wonky numbers come from. And just let me check. Yeah, up here we made a mistake. Instead of setting this uniform scale to 0.2, we set it to 0.4. And now that geometry is looking like I'd expect it to. Okay, this has some secondary objects scattered onto it using a scatter node, which will wire in after the poly extrude here. So scatter node goes in after that, like this. And that's a bit too many points here, and also it's scattered on the inside and the outside. So let's select only the extrude front group here, scattering only on the outside, dialing back the total count of points to say 20. The global seed, we dialed that in until it fit our distribution that we liked, in our case 1.69, and everything else left at default. Then we wrote a bit of vex to set the p-scale on those points. You can also do that with the attrib randomize or the attrib noise node. However, we are big fans of vex, so let's attach a point wrangle. And in here, the p-scale should be equal to a random value, which we're going to fit. And let's first generate that random value using the rand function. And as a seed, we'll use the point number times a seed that we dial in with a slider. And then map this value, which will be between 0 and 1, to two values that we call min and max, like this. Right, let's generate all those sliders, and it looks like I missed a closing parentheses like this. And in this case, again, lots of manually dialing in values until they matched a visual appearance that we liked. In this case, went with a seed of 0.25 and a max of 0.167 and a min of 0.07, like this. Again, just setting up random p-scale values between 0.07 and 0.167. Then wire that into a copy to points and use this points to instance a sphere onto them, which we just left at these default settings here. So that goes into the copy to points. And then we have these spheres sitting around our main sphere. So let's merge those two together using a merge node. with the remeshed main sphere going in here first, and then those secondary spheres going in here second, like this. Okay, let's blend all those together using VDBs. So I'm going to do a VDB from polygon and increase the resolution by decreasing the voxel size to a value of 0.019. Again, we dial that in just visually, so that's where these kind of wonky numbers come from, and then converted these back either using a VDB convert, or in this case we even just used a standard convert, and then again remeshing this with the target size being reduced again, something like this. Now it's finally time to start configuring this as a Vellum object. In this case we used a tetrahedral soft body. So I'm gonna drop down the Vellum configure tetrahedral soft body, which will create those two nodes, the tet conform and the constraints, and wire the output of the remesh into that tet conform here. So first we're gonna create all those tetrahedrons, which will then configure for Vellum use, including the constraints. In between here, I want to make sure I create another group, a pin group, where I can attach this object to whatever I want this thing to be attached to. So in between the tet conform and the Vellum constraints, I'll attach a group node, which I'll set to create a pin group, and it should be a point group. I want to disable the base group and instead use the bounding regions to define this group, then wire in the tet conform in here. And the bounding region here being a box, I moved over a bit to 0.32 something, I think. And then use that over again visually until I have a bunch of points selected. In this case, I ended up moving this to -0.718744, just to make sure we are on the same page as what we prepared here, just selecting these bunch of points in the back. And that goes into the Vellum tetrahedral soft body. In here, I just want to make sure that my values are set up as I prepared them. And in this case, I want to increase the stretch stiffness to a value of 1, not 0.01. I want to increase the damping ratio to a value of 0.2, and let's call the output group here not stretch, but tet stretch for tetrahedral stretch. And also let's increase the edge length scale to 0.9, like this. Alright, that's our Vellum tetrahedral constraint setup. And now let's first pin this group that we selected here so this doesn't fall down once we start the simulation. So after the tetrahedral stretch here goes another Vellum constraint, which will set up to be a pin to target constraint in here, working on the point groups, namely the pinpoint group that we created here. So now only those get selected, and we want to set the pin type to be soft. Same goes for the orientation pin type. And let's drag this down, scroll down here, and that is looking good. The only thing I want to do is increase the bend strength a bit, bend stiffness to exactly 1, and that's it. That's all I want to do in here. Okay, now one last thing. For this animation that we're planning, it should loop. That means this object here needs to return to its original state somehow. And for that, I'm going to use a second pin group, which I'll be animating, which drags this object here, this soft body object, back to its initial position periodically. And for that, I'll just attach another Vellum constraint, which again, I will set up to be a pin to target. And in this case, again, I want to work this on points, but this time all the points that are in here, so everything we got in here, and want to set the pin type to soft again. And then again, let's drag this down and scroll down here. Again, I want this to be soft, not permanent, like this. And then under the stiffness, let's set that to 1,000,000, the stretch stiffness that is, so not totally stiff, but very strong. And let's increase the damping ratio so it doesn't wobble around but settles quickly. Create a group for that. Let's call this one pin all, because we're using this to pin all the points together to its original position. And then for the bend constraints, I want to set this to be 1, and again increase the damping ratio to 0.3, and also create an output group for those and call those maybe pin bend all, or pin all bend, or something descriptive. So this should be our main geometry. Let's just attach two nulls here. Call one out. We call this thing PIM. I don't know what this should stand for. Again, received that file from Patrick, so let's just go with his nomenclature. Let's call one out pim and out pim constraint. Wire those in like this, and now we set this up. So again, everything until here is just creating this geometry. And then for the constraints, first we generated those tetrahedrons, then created a group where we want to pin this kind of permanently so it stays fixed, configured the tetrahedral soft body, then set up the pinning of the back here, and then set up a general pin group that includes every single point in this geometry to be able to pull this back periodically to its original position so we can loop the animation later. Now that's our main cocoon. Now the second thing we want to set up is the eggs, the balls, whatever you want to call this, that this thing produces. And for that, same as previously, we're going to start out with another sphere, again using the sphere create, generating a polygon. Let's just switch the view flag on this here and dial back its uniform scale to 0.28. And let's try moving that into this main geometry here by just moving up its center along the y-axis to, in our case, again, we did this visually, so a bit of a wonky number, 0.257405. Just so it sits roughly within that main geometry here. Also, let's increase its frequency so it gets a bit more resolution, and that'll be our geometry for these spheres here. This will be configured as Vellum balloons, so just by typing Vellum configure balloon and then hitting Shift Enter, we drop down these two constraints here. One is a cloth for the outer surface and one a pressure constraint, which tries to keep the balloon under pressure, keeping its shape. Let me just go through those settings for the Vellum cloth first. So in here, we increased the edge length scale a good bit to 0.9. Drag, we left at default, no pinned animation here. The stretch stiffness, we left at default here. Just renamed this output group here to sphere stretch to differentiate it from the other object. And our bend we left as is as well, just renaming that output group to sphere bend. Like this. Now for our Vellum pressure here, let's drag this up. We want this pressure to expand, so to push outwards like the balloon was being inflated. And for that, we'll just increase the rest length scale to 100. And also let's output this as a group and call this thing sphere pressure. So far. And before we output this to two nulls, let's just create those two nulls. Call one out sphere. Wire it into the first slot, and the second one, which we'll just copy and paste, out sphere constraints. Let's zoom out a bit like this, and this goes into the second slot here like so. So we have the constraints here, but I want to add a few attributes to the constraints. So I'm going to use a prim wrangle, a primitive wrangle, and in here on those individual constraints here, these lines, I want to set an age and a maximum age, which should both be a float. So f at age equals to 0.0 and f at max age, so the maximum age these things can have, should be 1.0, like this. And we will be using these parameters here, the attributes here, to determine how quickly those individual spheres that are created inside here should grow, should blow up. All right, that's our sphere like this. There's one last thing in here, one more detail, which is a bit of fluid that encapsulates this sphere here, which gets expelled together with the sphere as soon as it's created. And for that, I'll take my default sphere up here that I just created here and peek it a bit. So expand it to the outside using a peek node. Wire this in like this. Let's select the view flag on here. And I need two of those peek nodes. One set to expand this by 0.04 units, so quite substantially. And let's copy it and have the other one expand this only by 0.01 units, like so, just to create a film of fluid around that sphere and not a solid blob of fluid in which it sits. To do that, I'll take the first peak, the larger one, and use that to configure a Vellum fluid. And here in the Vellum fluid, I'll dial down the particle size a bit because this is rather large here, as you can imagine. So let's set this to 0.0075. Again, just a bunch of experimentation going on here to get at these values. Packing density and jitter scale are fine as are. And let's just dial down these physical attributes here. And let's decrease the density to 10 and give them a bit of viscosity, in our case 0.5, so they stick together a bit. Now, let's delete all those points which could potentially intersect our original sphere. That's this sphere here. And let's use the smaller peak here to select the grains here, fluid particles, for deletion using two group nodes. And we'll feed the peak into the second input here. Set this group node to work on points. Let's call it delete me. And let's disable the base group and instead check keep in bounding regions and set this to be a bounding object for points or vertices. And the points we want to select are the main particles, like so. So we hopefully have now selected a few of those inside particles. Let's just use a clip node to verify. And after we selected this group, let's just use a blast to get rid of the delete me group. And now we can see we hollowed out this particle sphere here. So that's after and that's before the blasting. And that's what we wanted. Okay, let's delete this clip, which was just there to check, and copy those two nodes here, paste them, and do the same thing for the constraints that we created here. So again, after and before deletion. All right, finally, let's take our main geometry here, the remaining points, and group them again, put them into a separate point group, which we're going to call fluid PTs for fluid points. Like this. In this case, let's just enable the base group and select everything there is. Okay, two more nulls and we are done creating all our geo. Let's call this one out underscore fluid grains. Copy and paste this, and let's wire this in here and call this one out underscore fluid constraints. like this. And I think we're ready now to set up our simulation. So again, 3 parts that we created here. Let's arrange that somewhat sensibly. I don't know what makes sense at this point anymore. Maybe something like this. Okay, 3 parts. The first one being our main object that expels those things here. Again, modeled using your standard VDB modeling techniques, and then set up using a tetrahedral soft body with a few pin groups. One to pin it at the back here and one to animate it back to its original position. Then we've got our spheres that are being expelled here, just as a Vellum balloon growing over time, set up to contain an age and maximum age attribute, which we're going to use to drive how fast those spheres will be inflated. And then finally, a bunch of fluids, film of fluid, set up as Vellum grains here, which surrounds those spheres that are created inside of the main object. Now it's finally time to set up our simulation, and for that we're going to drop down a dot network here. It's going to be a bit more elaborate than your standard default Vellum solver, so let's dive in here and set this up manually. What we're going to need is a bit of gravity, so that goes in here first, the gravity force, and in my experiments I wanted to dial this back a bit, otherwise it's going to become too drastic, so -3 on the y-axis is our fictional gravity for wherever this thing lives. And in here we're going to merge a bunch of stuff, so let's use a merge node. And the first thing I want to merge in here is a ground plane, so our newly formed spheres and liquid hit something once they fall. The ground plane, I want to move that down maybe 3 units here, like so. And then it's time to set up our Vellum solver. So Vellum solver, let's wire that into the merge as well. For the Vellum solver to work, we need a few things. First, we need a Vellum object to store the simulation data into, so Vellum object. This one goes into the first slot, and on our Vellum solver itself I'm going to set up the parameters now. Again, lots of trial and error to get those dialed in. So in the end, a substep count of 4 substeps with 24 constraint iterations seemed to do the trick for me, and under the advanced tab I think I left everything at default so far. Now, as you can imagine, there's a bunch of stuff going on in that simulation. And I want to drive that by a few nodes, which I will always merge into the second slot, in this case, like so. And the first thing I'll do is create a bunch of objects. The first being my sphere. So let's use a Vellum source, wire that into our merge in here, and let's create a sphere every 45 frames, which I can do with this expression. So if my current frame number, $ff, modulo 45 equals to 1, then this thing is true, and that happens every 45th frame. So if I click on that here, I can see the activation on the first frame is true, and then it gets to 0 for a bunch of times, except it hits 46, 92, 91, etc, etc, etc. Also, let's make sure the emission happens each frame. Again, we're only activating this every 45th frame, but nevertheless we need to have it set to each frame, so it will be evaluated not only on the first frame. Now, the geometry and the constraints we want to create, let's point it to that, clicking here on the sub path, and then let's go into our obj, our geo, and let's point it to the out sphere, and let's do the same thing for the constraint sub path, this time pointing it to the out sphere constraints, like this. Alright, so far for now, let's just go to the output here and hit play to see if that worked, and we can see we are creating this sphere which tries to expand immediately, then wobbles around a bit, falls down, and hopefully on the 46th frame we can see another sphere being created, and we can. Perfect. Okay, so far so good. The next thing that we need to create, and let's just copy and paste this Vellum source here, will be our main geometry, giving birth to all those spheres. Let's wire that in here and maybe change the order so they're front here. And in this case, we want the activation to be just 1 and happen only once. And in here, we want to create the out PIM and the out PIM constraints, like this. So if we hit play now, we should see something chaotic happening. Yeah, not too much, just this inner sphere trying to grow and being restricted by this outer soft body. Let's reset this, and again, copy the Vellum source one more time. Let's take this one here, the one where we created the spheres, and in this case I want to create the fluid object. So again, same timing as the spheres here, but only creating the fluid grains and the fluid constraints. Now, finally, let's start animating and driving this whole simulation. For this, let's just disable the first and the third source, so we can only work on this sphere here. And as mentioned, I want to drive the inflation of that sphere by its age and by its maximum age parameters. And for that, I'll be using a GeoWrangle set up to work on this sphere's constraints here. So that goes into the merge. And in the GeoWrangle's data bindings, let's set this to work on the constraint geometry. So capital C, constraint, capital G, geometry, like this. And then on the inputs here, let's set the first one to myself, no reads of outputs, like so. And the second input to DOP data. And the DOP data I care about is my geometry, so $, all caps, obj ID, this one here, / capital G, geometry, like this. And now in here, let's set this to primitives. I can write code that works only on this sphere's constraints. In here, I want to create one single parameter. Let's call this aging. And let's use a float slider, which we call aging speed. So that's how fast this thing ages, how fast it inflates. In my case, I set this to 0.075. That seemed a good value after a bit of experimentation. And then each frame here, what I want to do is create this age attribute that we created and initialize to be 0 to increase by this aging parameter, like this. Next, we want to clamp this parameter so it doesn't exceed our maximum age that we set. So in our case, it doesn't exceed 1. So let's use a clamp function and clamp this value to be between 0 and the maximum age we previously stored and created as an attribute on those constraints. And finally, just in case our max age isn't set to 1, I want to remap this to a scale value between 0 and 1. So let's call this one scale and use a fit function. In our case, with those current values, we wouldn't have to do the fitting. However, just in case if you change those values, make sure they are between 0 and 1. So we take our age attribute, which ranges between 0 as it was initialized and our max age, to which we clamped it, and then we remap it between 0.0 and 1.0. So it is always normalized. And finally, we take the rest length attribute we have on this constraints and set it to its original value. So f at rest length orig times the scale we just calculated. So fingers crossed, let's just hit play on that. And we can see it bouncing back once and then becoming bigger, increasing in size and oscillating downward. Okay, that's fine for now. So let's re-enable the other Vellum sources here. And let's animate these constraints that pull back this outer geometry periodically. So it loops. We're going to do that with a Vellum constraint properties, which goes in after the geometry wrangle in the merge here like this. And then I want this to only work on the pin all and pin bend all groups. Remember those groups that are there to pull this tetrahedral geometry back to its original position. The thing I want to animate here is a stiffness, and I want this to be periodically ramped every 45th frame with a bit of an offset to go from 0 to 1 and then sawtooth back to 0 again. Took me a bit of fiddling around with a bunch of formulas. In this case, what I want to do is take our current frame number, take the modulo of 15 with it, and then divide it by 15. And then multiply this by a rounded version of our current frame, modulo 45, divided by 60, and that should be it. So if we click on here and shift click on this value or inside this field here, we can get this curve display here, and we can see we're having exactly this sawtooth ramp that is slightly offset and ramps up in sync with the animation of our spheres here being created, being spawned. Now let's just save this and simulate this and see if that is working as we'd expect it to. So fingers crossed, let's check real-time toggle, hit play, and let's wait a bit. This won't be the fastest simulation, bunch of stuff to take care of, bunch of sub-steps. So let's see. Alright, that seems to work in a weirdly disgusting way. I don't know how Patrick got the idea for that, but I think it's really funny. One thing we could add for good measure might be a pop force down here that we can use to dial in a bit of noise, maybe for the fluid that gets expelled here, so that would be wired in here, but that is just for good measure for maybe adding a bit of wiggle, a bit of noise, if you like that, just by increasing the amplitude size for the noise here and dialing in those parameters. In this case, I will leave it at that, at least for the simulation part. And now for the output, I want to split this simulation part into the fluid and the other parts. So using a split node here and splitting that by the fluid points. So selecting the fluid PTs group here. So when I switch the view flag on here, I can see I only selected the fluid parts here. And in here, what I want to do is just attach a particle fluid surface to mesh those like this here. In this case, setting the particle separation up here to the same value as I set the particle separation up here where I created the vellum fluid. So I'll just right click on the particle size here, go to copy parameter, and then go down to my particle fluid surface here and paste this as a relative reference like this. Let's highlight this, and now we can see we are getting a surface here for those particles. Let me just check what else I did dial in here. I think that's all good. Just go to filtering, and I think I enabled the erosion by 2 units and smoothing this with a mean value in my case. That's that. Let's merge it together again with the original geo. So fluid goes in here, main geo goes in there, and now we've got this disgustingly weird simulation. As far as rendering goes, Patrick took care of that. I think he outdid himself with making this even weirder than it is in the viewport here. And for the magic he did with that, I will refer you to him. So please do not ask me about rendering this. I was only here to help with certain parts of the simulation. As always, I hope you enjoyed that. Again, just for repetition, 3 parts of geometry we set up in Vellum. The outer shell of this thing, the sphere that's being born, plus a bit of Vellum fluid, and then a bunch of animation happening inside of a DOP-net to drive the constraints of this, after which we separated the geometry to be able to mesh the fluid independently of the rest of the meshes. Hope you had fun. I'm not sure if I'm looking forward to seeing your artwork that you do using that technique, but nevertheless, just send it along. And until next time, it is cheers and goodbye.